A figure skater begins to spin. Her arms stretch outward. Her rotation is smooth and controlled. Then she pulls her arms close to her body. The change is immediate. She spins faster. No one gives her another push. There is no motor under the ice. The force that started the spin has already happened. So where does the extra speed come from? The answer is angular momentum. When something rotates, it has angular momentum. For a spinning body, this depends on two main things: how fast it rotates and how its mass is distributed around the rotation axis. Mass far from the axis is harder to spin. Mass close to the axis is easier to spin. When the skater's arms are extended, some of her mass is far from the center line of her body. Her moment of inertia is large. That means her rotation rate is lower. When she pulls her arms inward, that mass moves closer to the axis. Her moment of inertia becomes smaller. Because angular momentum is nearly conserved, her rotation rate increases. This does not mean she becomes lighter. Her mass is the same. It does not mean the ice suddenly pushes her faster. The ice mainly reduces friction, allowing the spin to continue with little resistance. The key change is the distribution of mass. Arms out, slower spin. Arms in, faster spin. The same effect appears in diving. A diver tucks the body to rotate quickly in the air, then opens the body to slow the rotation before entering the water. Gymnasts use the same principle during flips. A person sitting on a spinning chair can feel it by holding weights outward, then pulling them inward. The rule is consistent. Move mass inward, and rotation speeds up. Move mass outward, and rotation slows down. There is a common misconception that the skater speeds up because she simply pulls harder. That explanation is incomplete. Pulling the arms inward does require muscular work. The skater is not passive, but the work does not create angular momentum from nowhere. It changes the body's moment of inertia. The angular momentum remains nearly the same because there is little external torque around the vertical axis. Rotational kinetic energy can increase during this process because the skater does work while pulling the arms inward. But angular momentum is still conserved. This distinction matters. Energy and angular momentum are related, but they are not the same thing. The visual effect is striking because the body itself becomes the control system. A long, spread-out shape resists fast rotation. A compact shape rotates more easily. This is why body position is so important in sports. Skaters, divers, dancers, and gymnasts all use shape to control motion. They are not escaping physics. They are using it precisely. The skater's spin looks graceful because the motion is smooth, but underneath the elegance is a strict conservation law. She starts with angular momentum. She changes her shape. The spin rate changes in response. No hidden push and no violation of mechanics. Just a human body showing one of physics' clearest rules on ice.